Hello and welcome to this session on verifiable computing. My name is Ahto Truu. I work as a software architect at a company called Guardtime. And like the title says, today here I'll try to talk a little bit, give a little introduction into the topic of verifiable computing. And since I'm here as a representative of my company, so a bit about Guardtime also. We are a systems engineering company focusing on data security solutions, which is also why I'm interested in this verifiability business. And you can read how we are pretty old, not a startup anymore, founded already 15 years ago. And our first product was a blockchain-based timestamping data integrity service, which is still running. And I'm proud to tell you, our blockchain is a year older than Bitcoin. So contrary to popular belief, Bitcoin was not the first blockchain in the world, though they did coin the term. So for the first couple of years, we did not use the word blockchain for our technology because the word had not been invented yet. And just in case you had any doubts, yes, we are hiring. So if any of what I talk about today sounds cool or interesting, do check out our jobs page. But let's go on to the meat of the talk. So as you can expect, I plan to start telling you why verifiable computing is something of interest in the first place. Then we have to look at some generic cryptographic tools which are not specific to verifiable computing in any way, but we're going to need them, and they tend not to be quite common knowledge among all programmers. So just in case, let's go through some reminders for those who have heard about those before, and then quick intro for those who haven't. And then we look at arithmetic circuits and programs, arithmetic programs, which are mathematical ways of modeling programs and behavior, and which are used at least in one particular verifiable computation system, which then finally we have all the preliminaries, and we can look at how this verifiable computation thing is done actually. And then hopefully in the end it will all make some sense. So for the motivation, verifiable computing is a model of computing where a client wants to outsource some work to a server. And then the client doesn't necessarily want to trust the server to do its bidding correctly. So when the server returns the results of the computation, the server also returns a proof that the results are correct, that the computation was carried out correctly as a client had requested. If you go and look at papers and blog posts and discussions of these topics, and it also has been sometimes called certified computation, even though the certified part is also, the word is also used in other meanings, like certified hardware or certified software, in the sense that some auditor has had a look at the software and approved it, which is quite distinct. So, but the certified computation word has also been used in the meaning of verifiable computation. Delegation of computation, again, it sounds more generic or more general. You can delegate without the proof part, but this also has been used for the verifiable computing model. And also the word or the term computational integrity has been used. So these are all can be the same thing, but you have to read the fine print. Some of them also have other meanings, some of those expressions. One example, perhaps a bit more specialized example of verifiable computation is a field of research called authenticated data structures, where specifically the server doesn't do any general purpose or any generic computations for the client, but maintains a database. And then the model is still the same. For every update request that the client sends to the server, where the client asks the server to change something in the database, the server sends back a proof that the change that the client asked for was made, and also a proof that nothing else was changed. So, and then for every query, when the client asks something wants to retrieve something from the database, also the result comes with a proof that the result matches the current state of the database. I did a talk about this more specialized version of verifiable computing when the conference was live last time, which must have been 2019. So if you want to have some more discussion of this specifically, one option is to go into the ACCU conference video archives and dig out the 3 years old talk from there. But today we are going to talk about more general model, more general outsourcing more general computations to the server in such a verifiable manner. And examples of this are a client just outsourcing work to some cloud service provider, because cloud is this infinite number of computers with infinite computation capabilities, and so it's nice to make use of those. Another model which sometimes is also considered as a useful example is IoT devices supported by some external servers under the premise that IoT devices, they are some small underpowered sensors and don't necessarily have the capabilities to do all the computations that are needed, but maybe, and this is maybe a more uncertain or not so clear case. I would normally expect that the servers, that the IoT devices outsource their work are part of the same system, and kind of the sensors might be trusting the servers, but maybe there are also some more heterogeneous networks where the small edge devices and the servers are operated by different parties which don't necessarily trust each other so much. So this is also one possible application of this verifiable computing system model. And one quite more recent motivator for these kinds of computational models and research into them is smart contracts executed on a blockchain. Because by default, just in case a smart contract basically is a piece of program code that is posted to the blockchain, and then when some data is posted addressed to that piece of code on the same blockchain, then the code executes and in turn can post results on the blockchain. And then when somebody wants to verify that the actions carried out are correct, then the standard model currently basically is that every verifier, every party, every user of the blockchain who wants to verify the integrity of the activities on the chain, they have to rerun the computation to verify that when the contract code is executed on those given inputs, the results are as claimed. And this means that if a blockchain has 1 million clients, then the computation is executed 1 million times, and this is quite wasteful. So one modern motivation for this verifiable computing is that the actual execution of the smart contract can be done off the chain, and then only the results with proof of correctness can be posted to the chain, and then of course this model is useful only in case when the verification is cheaper than just executing the program in the first place. And for some types of computations, this disparity of doing the work and verifying the work comes naturally. There are a lot of combinatorial problems where coming up with a solution is computationally much more expensive than verifying that the solution is correct. There is also quite a lot of cases in solving various equations where solving of an equation or a system of equations is much more expensive computationally than once the solution is found, verifying that the solution is correct, that it satisfies the equation. And But if you want to do this verifiable computing thing in some more generic setting outside of those special cases of problems where the verification is naturally cheaper, then there needs to be some extra work done on the server side to generate the proof of correctness of the result in addition to the result itself, and then the proof can be carried back to the client or posted back to the blockchain in the third motivating use case. And then everybody who cares can verify that the result is correct. So one thing also that comes up in context with those verifiable computations, because already cryptography is involved and people start to think about those things, and it turns out it is possible also to do something about this, is integrity versus confidentiality. So if we're already using cryptography to ensure integrity of the results of the computation, we can also start thinking about confidentiality of the data, where it is possible to imagine quite a lot of applications of computing where at least some parts of the data are confidential, but we would still like to be reasonably sure that the outcome or the results are correct. And of course, very prominent or easily understandable example in all democratic contexts is verifiable electronic voting. The votes themselves are confidential, but the public needs some assurance that those confidential votes were tallied correctly and the result of the election is valid. So this kind of thing. There is also a model that has been studied for this confidentiality as an example is privacy preserving meta readings. So if some community of homeowners has electronic automatic meters for gas, electricity, things like that, they might be interested in aggregating the readings and submitting and reporting the result to the utility company and getting a bill. But they might at the same time be interested in keeping the individual readings confidential because they reveal usage patterns, and some people consider this somewhat a privacy invasion, especially considering that the automatic meters often they measure they take the readings with much higher frequencies than the manual reporting, which usually is done once a month and doesn't really reveal anything about the usage patterns as such. And then, of course, again, we come back to the blockchain topic where normal standard practice is that all details of all transactions are posted publicly on the chain and are visible to every user of the chain, which, of course, is a privacy disaster. And then this is a good motivation also to study this confidentiality aspect, where it is possible to execute the transactions privately off-chain, but still provide publicly verifiable proof that whatever was done in this private transaction was legal and valid according to the business rules that have been established on the chain. A typical example is just payment, where it is possible to prove that the money that was transferred, the payer owns this money initially, and it has been transferred to the payee, and the amount has not changed. So in the process of transferring this money, there was no money was lost, which probably other users of the system don't mind so much about, but most importantly, no new money was generated. So this is what other people would mind if you were able to print money in those private transactions, and the value of the other people's money would thus correspondingly go down, and they obviously would not like that. So this is also a prime motivating example, and actually quite a lot of those verifiable and privacy preserving computation research in the last few years has been funded by blockchain companies. So this is they have the business motivation to get the results, and they also have the means to invest into this research. So this is in short why we care, at least why some people care about this kind of computation model. And now let's look at what the building blocks are that we can use to build such a system. And I already mentioned before that some problems have naturally this property that finding a solution is much more expensive than verifying the solution once you have found it, and that many equation solving problems or equation solving tasks are of this kind. And one example is the problem of computing discrete logarithms. So the problem in a nutshell is you are given 3 numbers, m, g, and y, and you are asked to find x such that the g to the power of x modulo m equals y. So if you scratch out the modulo part here from this equation, then it becomes a standard exponential equation. You just, if it is on real numbers, you just compute the logarithm of y on the base g, and you have your x. If you do it in integers, then it's actually perhaps even easier. Multiplying or squaring an integer usually scales the length of the integer by correspondingly. So you can just take the length of g to the power of x divided by the length of y, and there is a pretty good approximation of what the x should be. And then you can, in case it doesn't come out as an even number or a precise integer, you can try the upper and lower, round up, round down, and one of those two must be the correct answer. So in this non-modular case, the equation is trivial to solve. But in the modular case, because then in the modular case, the powers, when the values of x go up, the powers start to wrap around. And so the size of the value no longer correlates with the value of x. So the size of the value of g to x no longer correlates with the size of the value of x. So you cannot do this division of lengths. You can't really do. Well, there are techniques which are more efficient than just trying all possible values of x one by one, but still it is very expensive to solve those equations when the x is potentially a large value. But once you have the solution, you can of course efficiently verify it using the standard square and multiply exponentiation algorithm. And just in case you haven't heard of this method, then you basically view the power as a binary number, and then just as you compute the value in a binary system, you can use basically the same algorithm to compute the power. First, you compute by repeated squaring, you compute the powers of the g that correspond to powers of 2. So g squared is g squared squared is g to the 4th, g4 squared is g to the 8th, and so on. And then you go and multiply together those powers of g that correspond to the set bits in the binary representation of x, and you have the result. And this means that there is this exponential difference in difficulty in solving the equation, where you basically have to try all the values of x, and then verifying the solution where the number of operations you have to do is proportional to the length of x, not to the value of x in binary. So this creates this big disparity, and this problem, in fact, has been used as a building block in many cryptographic solutions and protocols. So this is a very, very famous and much used workhorse in cryptography. And one thing that is quite specific cryptographic tool is cryptographic commitments. And these are also used in this verifiable and privacy preserving computation protocols. So basically, this cryptographic commitment is a way to commit to some value without disclosing this value. So a motivating example might be if you want to run. If you want to take bets in office with friends on the results of the football game, everybody makes a bet, well, now we are starting to get back to offices, so maybe we can go back to the old method where everybody writes a prediction on a piece of paper and throws it into a bowl, and then on Monday when you come into the office, you open the bowl, and then you can see who was the best predictor of the result of the game. But if you want to do this same thing electronically, then the technique to use is cryptographic commitment, where everybody posts publicly, let's say to the company chat or mailing list or whatever you use, a commitment of their prediction. And then on Monday, everybody opens their prediction, and the two properties that are required of the cryptographic commitment protocol or mechanism are binding and hiding. So binding property means that if you on Friday, if you predicted that the result of the game is a tie 0-0 and computed a commitment of that prediction and posted it to the chat, then you cannot on Monday you cannot come up with a way of saying that, okay, I predicted that the result will be 3-2 because the game actually on Saturday ended with this score. But you might want to make this claim, but you would not be able to link this changed claim to the commitments that you posted on Friday. So this is a binding property. Once the commitment has been computed, the input cannot be changed anymore without breaking the relationship between the commitment and the input. And in order to prevent people from copying their solutions from others or learning how others have predicted before the correct time, then the commitment should also have this hiding property, which means that by looking at why, it is impossible to find out what the X was. And this difficulty of the discrete logarithm problem can be used to obtain a cryptographic commitment protocol. And the naive way is as a commitment, we just we pick some number G. Everybody can use the same number, everybody within the same system. And we pick two parameters, G and M, which are the so-called public parameters of the commitment scheme. And then a commitment in a naive case can be just G to the power of X modulo M. We know it's normally difficult to go from this computed value back to X. So we can post this Y on the company chat, and others would not be able to, normally should not be able to reverse this transformation to recover my prediction until I publish it myself on Monday. A weakness of this naive protocol is that even though in general reversing this modular explanation is computationally very expensive, in case of those football results, there are just so few inputs. So it's very rare for a football game in a football game for either side to score more than 10 goals. So this basically means that realistically possible results go from 0-0 to 10-10, and then even 10-10 you probably wouldn't call it realistic in most contexts and most games. But even if you consider this, then this means that there are basically 121 possible outcomes of a football game, and this means that if you have made your prediction and posted the commitment to the company chat, I can just try all the possible 121 possible inputs, compute the same commitment, and see what the commitment would be if you had made this prediction. And then one of those will match what you have posted, and then without actually breaking the difficulty of the logarithm problem, I have discovered your input. And again, this is a standard method in cryptography to protect these kinds of low entropy inputs, is to add some randomness deliberately to it. So to mix in some extra randomness so that the low entropy of the to mask or cover the low entropy of the actual input. And then this gives us so-called Pedersen commitments after the scientists that first proposed them, was that, and this idea is that instead of just posting G to the power of X, and instead of just having G and M as a public parameters of the commitment scheme, we have now G, H, and M, 3 public parameters, and everybody to post a commitment of their prediction X, they additionally just pick a random number R, and then they post as a commitment this slightly more result of this slightly more complicated expression. And the idea here is that this H to the R, if R is a random number picked from a sufficiently large range, then try for an attacker to try also a combination of X and R, which they would now need to put in both of those to make a guess and verify whether that guess is correct or not. Then if the range of R is large enough, this becomes infeasibly difficult for the attacker to break the hiding property. And one interesting thing to observe is that in both in this naive case and in this Pedersen commitment case, this commitment actually has some algebraic properties. So if you have a commitment of value x1 and a commitment of value of x2, you can compute the commitment of the value x1 plus x2 without actually knowing what x1 and x2 are. So you can do some computations on the commitments without knowing what the underlying values are. But you know that the value that the resulting commitment is binding and committed to this sum value. So this is perhaps something that is not an expected property if you have already spent so much effort in making sure that the commitment scheme is hiding, which means that you can't get the input out of the commitment value, but you can still do math on those commitment values. And this math will be in some potentially useful ways related to the math on the underlying input values. So zero knowledge proofs. This is a final thing before we get to the actual computational part. So zero knowledge proof is this concept that you want to prove that you know something, but you do not want in this. So a simple way to know that to prove that you know something is just to say it out. But if you don't want to reveal that something, but still prove to the other parties that you know the value. So this is what is called zero knowledge proof in cryptography. And one example is digital signatures. So to create a digital signature, you need to be in possession of a private key, and then the signature would verify with a corresponding public key. So anybody who has access to the public key can use the public key, verify the signature, and this is basically a proof that you know the private key. If you were able to produce the signature correctly, then you must know the private key. But the key itself is not revealed in the process. So the verifier will have access to the public key and the signature, but and this is a standard security property of a digital signature scheme that just having the public key and the signature, it should be infeasible to recover the private key from those things. Otherwise, the signature scheme is considered broken. And in some ways, just the same example as we already had on the previous slide about the commitment schemes, in some ways, this can also be considered as a special case of zero knowledge proof. So I can present the 3 commitments, and this constitutes a proof that the value here under this commitment is a sum of the value of here under this commitment and under this commitment. But the verifier can receive those 3 commitments and verify that the multiplication between those 2 commitments really gives a 3rd commitment. So this is proof that the underlying addition holds. But it does not reveal anything about the values of either the addends or the sum. So this can also be viewed as a special case of a zero knowledge proof. I prove you that I have a solution to this equation, but I don't give you the particular values that I have as solution. So this is a final. Oh, I'm sorry, I forgot. This is a final cryptographic thing. We also, in the construction of the verifiable computing scheme, we also need one thing which is pure algebra, which is not very specific to cryptography. And this is called bilinear mapping. So bilinear mapping is a function on two arguments, of which are the arguments are usually from one set, and then the result can be in the same set or in a different set. And both the G1 and G2, they need to be an algebraic structure that is called a group, which is why they are indicated by G here. And the map is bilinear if the effect of multiplying either of the inputs with a value carries over to the value in the function value. So if you consider the value of applying this function to x and y, and then you multiply the x with a constant or the y with a constant, then those constants can be carried out from the expression from under the function application into so they have the same effect, linear effect on the value of the function. And the first kind of standard way is when both the source group, the G1, and the target group, G2, if they are additive groups. So if the operation in the group is adding two elements of the group, two numbers, then this form is used for the bilinear property. And if the output or the target group is multiplicative, so the operation in that target group is multiplication of two elements, then this rule changes. So here the operation between group elements here is adding, and this means that the factors become factors also. So it goes from addition to multiplication. So basically one level up in the hierarchy of operations. And here, if the normal operation between elements in this group G2 is multiplication, so the factors go from being multipliers to being exponents, which is again one level up from in the hierarchy of operations. And now we have covered the underlying atomic building blocks from cryptography and mathematics, and we can start looking at computing models. And the first thing that we consider is arithmetic circuits, which are an abstract representation of computation. So you probably, being computer science people, you have all at least on some level you are familiar with normal logic circuits where wires represent Boolean values, and then the gates on those wires represent logical operations and or not XOR whatever. Now, arithmetic circuits are in principle similar beasts, but for arithmetic expressions instead of Boolean expressions. So the wire values are numbers, and the gates are additions and multiplications. And as an example, the circuit here represents the expression C1 plus C2, multiplied by, so this element here is a sum of C1 and C2. This element here is a product of C3 and C4, and this is a product of those two sub-expressions. So kind of like the abstract syntax trees in the belly of a compiler, which might also be a familiar thing to many people here in the audience. And one thing you perhaps can notice here is that this circuit model, since it is a fixed rigid structure, it doesn't have loops. And when a computation is converted or encoded as an arithmetic circuit, loops must be unrolled by the compiler or by the conversion routine. There are also no conditionals, at least not in the standard arithmetic circuits, but conditionals can be modeled. So the conditional, the expression of if A is true, then return B, otherwise return C. This can be replaced with this expression A times B plus 1 minus A times C. It's quite easy to verify. If A is 1, then this second term here, this one becomes 0, so this cancels out, and the result is B. And if the value of A is 0, then this term cancels out, and the result is C. So depending on whether A is 1 or 0, you get either B or C. So it effectively, the expression here works like a conditional, even though it looks like an algebraic expression. And this can be represented as a circuit. So this is how conditionals are, how conditionals are encoded in those circuits. And for computer science theory, it is known that polynomial-sized arithmetic circuits, their computational expressivity is the same as polynomial time Turing machines. So pretty much everything can be in one way or another encoded as arithmetic circuits, pretty much every computation. Now, this starts to get a bit more complicated. Quadratic arithmetic programs are a way also a way of representing computations. And it's very difficult to explain, to go with explanation from a normal program source code straight into the quadratic arithmetic programs, or QAPs as they are often called for short. So usually the transformation is done both in explaining and also in implementation. The transformation is done so that whatever source form your computation is, you first translate it into an arithmetic expression, and then you construct the corresponding QAP. And the QAP is constructed as follows. So first you take your original, it's a bit too sensitive. So first you take your original expression, your original arithmetic circuit, and in addition to inputs, which we already had labeled so that we could highlight what the computation is, or write down the expression of what this tree is representing. And you also add labels to the output wires of our multiplication gates. The addition gates, we neglect them, we don't number, we don't label them. And then for each output wire of a multiplication gate, so each of those newly labeled wires, you pick an arbitrary, which is called root, and which is why it's marked as R. And each of them, the only requirement on them is that they have to be distinct. So there has to be a distinct root value dedicated to each of the output wires. Of course, if you have a large computation, then the circuit will be large. There will be many multiplication nodes or multiplication gates in it. So you will need to label all of them, and then you need a large number of distinct values. But luckily, the numbers that we are considering here, at least in cryptographic context, we are talking about numbers which are 100 bits or 200 bits or perhaps even longer. This is required, so this large scale is required for security margins. If the possible inputs are too small, then again, in the end, the verifiability of the whole system will suffer, because an attacker could fake a proof by just doing a brute force search over all possible parameters. So we are talking here about really large numbers. And so there is no risk whatsoever that you will run out of possible values. And then you pick for each of those six labeled wires, you pick 3 polynomials. And you can think of the polynomials here as weights. So this V is the weight that any wire contributes to the input of any multiplication gate. And so the polynomial V1 should be picked such that when it is applied to the value R5, then it evaluates to 0, and when it is applied to the value R6, then it evaluates to 1. So this is how you read this table. And the meaning of it is that if you look through the addition table, you will see that this input via C1 contributes as a left side input to this R6 with a weight 1. So it counts once as an input to this gate. And likewise the same, the C2 coming through this addition, it also counts once as a left-hand side input to this gate. So maybe it would be better to start the explanation from this multiplication gate where we have like input wires going straight into it. And this is why both, this C3 is a left-hand side input to this gate that produces C5. So this means that the V3, when evaluated on the value R5, must yield 1. And similarly, the W's are for the weights of the right-hand side inputs. So C4 is an input or the right-hand side input to the same C5 gate. So the polynomial V4 evaluated on the value R5, I'm sorry, should be 1. So these are those two elements, the one here and the one here, they indicate that those C3 and C4 are the two inputs to this gate. And then Y is labeling of which wire is the output of which gate. So this C5 wire is the output of this gate. So this means that this polynomial Y5 is 0 on all other values and 1 only on this. Did I get this right? I think I may have mixed up the values here in this table. I think it should be 1, 0 here and 0, 1 here. But basically the idea is the same, whether it is contributes to the value of this wire or not. And the multiplication ones, the input goes straight in here, and the addition gates, like in labeling, we ignored them, and we ignored them because we let them pass through. So we count this C1 as contributing to the input of this C6 gate, and we don't consider, we kind of ignore in this representation, we ignore the addition gates. Instead, we just write up that both C1 and C2 are inputs to the C6 gate on this left-hand side wire. Because the value on the left-hand side wire of C6 is C1 plus C2. So they both contribute with weight 1. And the other values, the C3, 3, 4, C5, none of them contributes to this wire. So all the other weights are zeros. And the only requirement, so the polynomials can be arbitrary polynomials. The only requirement is that when this polynomial V1 is evaluated at the argument value of R5, it needs to evaluate to 0, and when it is evaluated at the argument value R6, it needs to evaluate to 1. This means that since the polynomial we only have requirements on 2 points on this polynomial, the simplest and easiest form of the polynomial is just a straight line going through those 2 points. So the polynomial basically can be a function whose graph is a line which goes through the points R5, 0 and R6, 1. And this we can pick. We could pick more complicated polynomials, but to keep things from blowing up, actually the linear ones, of course, are most useful. And so this is what you should pick if you want to optimize your solution. And now, why you would do this? As a next step, we define one large polynomial as this kind of this px, as this quite complicated and scary looking expression. But if you look at this expression for a few minutes, then perhaps you will notice that this one here, actually, if you evaluate this part of the expression by plugging in R5 for x, then this basically yields you C1 plus C2, because all the other values here are zeros in this column. And the same way, if you do this one, it only gives you, this one evaluates to C5. And so basically this means that this is a complicated way of adding up all the inputs that contribute the sum of inputs on the left input wire of any gate, and this is sum of inputs on the right hand input wire of any gate, and this component is the value of the output value on the same gate. When you plug in either R5 which was the root related to this gate C5, or R6, which is the root related to this gate. And we are only ever going to be interested in the value of the polynomial on those gates, so we don't care about others. So this basically, what we have done now is we have arrived at a very complicated way of representing basically the truth value of whether the claim that if we put this C1, C2, C4, and C3 as inputs to this gate, what the C5 and C6 should be. So if we want to test a claim that this assignment means that the arithmetic circuit has been evaluated correctly, this happens if and only if this expression here is zero. It has this property. So it's quite a bit to wrap your head around. I know when I first read the paper that describes this thing, it took me quite a while to understand that this actually is the case. But since then, I had time to contemplate this, and I have become convinced that indeed this is the case. And so this means that this P, when evaluated, when the constant values C1 to C6 are fixed, then the P is evaluated on those values, then it is zero if the assignment is in agreement with what the arithmetic circuit should compute, and it is something else if it is not. And additionally, something called the target polynomial is defined, which is another polynomial which is zero exactly when on those values which correspond to the roots of those that we associated with those wires here earlier in our construction. And now the next thing is that what we do, instead of saying anything about evaluating the p x on specific values of x or t on specific values of x, we require that the polynomial tx divides px without a reminder. So there is, I hope this is common enough knowledge that polynomials can be divided just like integers, and they may, just like integers, they may divide each other evenly without a residue, or there might be a residue. And so by definition, the quadratic arithmetic program has been evaluated correctly if this division comes out without a reminder, and the reason why this is basically the same as the claims that this characteristic polynomial p, when evaluated on R5 or R6, becomes zero with a correct assignment, is equal, because the only way a polynomial can, the only way how the polynomial tx can divide px is if all the factors of tx are also all factors of px. This is just the same like with integers. If you have two integers a and b is even, and B divides A, then A also has to be even. So if B is a divisor of A, then A has contained all the prime factors of B for the division to be possible without a remainder. And basically those monomial elements here, x minus a constant value, they behave like in the realm of polynomials. Those monomial elements, they behave like prime numbers in the realm of integers. So this is basically the representation of kind of like a product of two primes. And this is a representation of another number, and this other number is divisible by this number only if it contains as elements or as factors those two primes. And this is exactly what we want. If it contains those elements as factors, this means that when we evaluate this larger polynomial by plugging in R5 or R6 for x, then this necessarily means that one of the terms in this, one of the multiplicative terms in this polynomial is also 0, and it doesn't matter what the other things are, the whole polynomial also has to be 0. But this is a more compact way in some ways of representing the same factors, the same requirement, and this is what is going to be exploited in making the proofs more compact. So how we are doing for time? Oh, I think we are doing just fine. Okay, so verifiable computations. Now, a formal definition of a verifiable computation system. There are such more formal definitions also for commitment schemes and signatures and zero-knowledge proofs and everything else that we kind of informally in a hand-wavy way looked at before. But since this is going to be, this is a main thing that the talk is about, I think we should be more precise and accurate in defining this. And so as a formal definition of a verifiable computation scheme is that it consists of three functions. The first function is key generation, which generates, gets the f is a function that we want to compute. So this is mathematically speaking, this is a mathematical function object, which can be represented as a piece of C code, or perhaps a C function, or as an arithmetic circuit, or as a quadratic arithmetic program, as we saw in the last couple of slides. But mathematically speaking, this is just a function. And the key generation then takes this function as an input and generates keys corresponding to this function, and it generates two keys. The first one is the evaluation key, which is something that is needed by the server or the worker when it starts computing the function on behalf of the user and producing a proof that the computation was done correctly. And the other one is the VK. This is a verification key, which is what a verifier would then use to verify that the proof is correct. And just like in a digital signature systems, the private key and public key come in pairs, and the signature made with a private key can be verified with the corresponding public key. Those evaluation and verification keys also come in pairs. So a proof produced with the evaluation key can be verified with the matching verification key. And so this is the key generation setup. This has to be done just once when the function is defined. So this is a one-time effort. So if you have like a standard smart contract that you post to your blockchain, you do this key generation once, and then those keys kind of become part of the definition of the function. So you don't need to redo this key generation part every time you want to evaluate the function on another set of inputs. And now to compute the function on a set of inputs, then the evaluation key is one of the things that is given to the computer or to the worker or to the server that is performing this computation, and then U is the user input to the function. So basically what the server then upon this needs to compute is it needs to apply f to the arguments U and produce y as a value, and in addition the proof by y, basically the proof that the value y was computed correctly. So these are the two outputs. First is the result of evaluating f on the input u. And second one is the proof that the evaluation was done correctly. And then the verification function gets 4 parameters, 4 inputs. First one is a verification key from this key generation phase. Then the u, the input on which the function was evaluated. The y, which is the claimed value of the function when evaluated on the input u. And pi, which is the proof that y was computed correctly. And if the verification of the proof confirms that it was indeed computed correctly, then the verify function returns 1 or true. And if not, the verification function returns 0 or false. So this is a cryptographic mathematical formulation of what it means to be a verifiable computation system. And now Pinocchio is one particular implementation of a verifiable computation system. It is a joint work of researchers from Microsoft Research and IBM Research, and it is perhaps heartwarming to people here at the ACCU conference that unlike many other scientific prototypes, it actually takes a subset of C as input and not Haskell or any other more mathematically oriented language. So it implements a substantial subset of C as input. You give a function written in C that has some parameters and computes some value, and then this is converted. The C code input is first converted into an arithmetic circuit and then into this quadratic arithmetic program representation. And then from there, it is this tool, Pinocchio tool, generates programs for key generation for the computer and prover, and then the verifier. So you get as output 3 programs. And Pinocchio in particular is actually, practically speaking, it is now quite old. It came out in 2013, so it's 9 years old already. There are 2 reasons why I chose to specifically talk about Pinocchio here today. First is that even though there are more efficient and more capable systems now developed in the intervening 9 years, Pinocchio is reasonably explainable. Everything more modern. If you think what we did and what we are going to see here in a couple of next slides, if you think this is complicated, then the newer things are even more complicated. So this is one thing, and another thing is that this is actually historically a milestone result. This was the first time ever that a verifier was actually faster than a native execution of the same code compiled with a reasonably recent C compiler. So there have been theoretical models where the asymptotic theoretical complexity of the verification algorithm has been better. Like you can have a verification run in time which is logarithmic compared to the runtime of the program that was executed, but the constants were so horrible that anything that you could possibly compute in this lifetime, for those things still, even if the verification was theoretically logarithmic complexity, it was still running much slower than the actual just takes the thing and execute it. But with Pinocchio, for first time, the verification was actually faster than just executing the compiled C code to compute the output directly. But it does come with quite complex implementation. It is not easy to achieve. So I think it is not a reasonable exercise to try to go through all of those elements and indices one by one and try to verify that the thing actually is consistent and secure and whatever. I will give you a reference to the original paper. You can read it, and you can also, if you feel like trying it out, you can take the prototype implementation and play around with it. But just to give a little bit of a taste or flavor of how this thing works and what it does. So this is f is a function that we want to evaluate, and then it is the key generation parts and how they work. The f and this is just a reminder what the definition of the key generation function is. What the two things are that it needs to output. So this is from the formal definition of a verifiable computation system. So f is a function that is to be evaluated, and this is translated into an arithmetic circuit, and the circuit is converted into a quadratic arithmetic program. And from this quadratic arithmetic program, we have those 4 elements then that we need to take out. We have this target polynomial. So inside of this key generation, the R5 and R6, those roots are chosen, but the roots themselves, they don't really come out as separate elements. So they are internal tools in constructing this thing. The main thing that comes out is the TX, which is the target polynomial, the one that had to be a divisor of the big polynomial. And then the elements that make up the coefficients of the big program. So the V's are the weights here, and the W is a set of the weights here, and then the capital Y is a set of those lowercase y's here, roughly speaking. And then the indices of the labels, the indices of the labels here are divided into 2 groups. The capital I with the IO is those wires which are either inputs or outputs of the circuit. So in case of this very small circuit, C1 to C4 are inputs and C6 is output. And then I mid is the middle wires, the ones which are not inputs or outputs. So in this small example that we have here on the slides, C5 wire is the only middle wire. And there is distinction between those because the inputs and outputs, the values on the input and output wires are visible. So some of them are the inputs that the user gives, and some of them are the outputs that the server computes and returns. But we also need, in these expressions below on how the proof is constructed, we also need to refer to the internal, the values of the internal wires, which the server computes, but does not give to the user because these are internals of the program, of the execution of the program. They are not the result. So these are somehow hidden from the client. And they are treated differently in this proof system because they are not visible to the client. So the fact that they have been computed correctly has to be proven slightly differently. And then additionally, E is a bilinear mapping. The one in the mathematical foundation section of the talk, which I almost forgot to tell you about. Good thing I had a slide to remind me. And then G is so-called generator. So this is one element in the group that's bilinear mapping maps the pairs into. So this is an element of this G2 group from the definition of the bilinear mapping. And so this is the evaluation. This is the conversion of the circuit to the QAP, basically, and then some additional parameters that have to be defined. So E and G, they don't have to be generated freshly for each circuit. So they can be fixed as a general parameter of the whole system once and for all. But mathematically, there is freedom. You can choose them. Just like the polynomials V, you can choose them in multiple ways. But in a particular implementation, you have to choose some way how to do it. But in theory, the system works with any choice, as long as the requirements are met. So the V here has to evaluate to the right values here on those parameters. And then the key generation picks a few more parameters and then computes a bunch of powers. And you can see there is a lot of exponentiation going on here. So a lot of things are here. G, this generator element, is raised to this power, to that power, to this power. And without going into the details of all of those bits here, the important thing is that those powers are generated with the purpose that the powers are given to the verifier, but the exponents are not. Which means that whatever things the server that is evaluating the functions, that is running the program for the client. So those powers are given to the server, but the exponents are not given to the server. And this means that whatever things the server computes, the server basically can only do the G values. The server can compute new elements of this group from which G comes only by combining the elements that he has been given. So he can compute G to the power RV plus RW by multiplying those two elements. But he does not learn what the RV and RW are, and therefore he cannot do anything else with those RV and RW values. And the evaluation key, those brackets, those things in those curly brackets, they are actually sets of things which iterates over all of those Ks here in this VK. So those Vs here are evaluated across. So V1 is evaluated, V2 is evaluated, and you have this set of elements here. And likewise for the Ws, you do all of those Ws from this column here, and you have this set of elements where again the K ranges from 1 to 6 in this particular case, but over a much larger set of values for a larger circuit. And the verification key, a good thing to note here is that the verification key is much smaller. So the evaluation key is something that only the client and the server need, but the verification key, in case you want to have public verifiability like in blockchain, the verification key is something that you need to post to the blockchain. And this is a good thing that this is much smaller. So these are all individual elements. So this is one element, the G itself. This is G risen to the power alpha. So this is again one element of the group. And the only thing where you have a family or a set of elements is here, and this only contains K elements. So the verification key size is linear in the size of the program that you want to represent in this verifiable computing system. So evaluation and construction of the proof, still more exponentiation. So the small bit here is that the server computes what is the value of the function when applied to the input given by the client. And in the process, the server, because the evaluation is done in terms of this arithmetic circuit, in the process, the server learns what the CI values for all the wires in the input in the circuit are. So for all of those wires, the server, as part of computing the function, maybe I should have left the figure here as well, learns what the CI values are. And then the CI values are going to be used here in the construction of the proof. So the CI values, maybe I should have put CK here also for the indexes to be consistent. So they are used here. So those values V mid, this is defined as a linear combination of those internal invisible wire values. And then the proof is about things, again, elements in this target group or range group of the bilinear mapping, which can be computed based on the inputs that were in those GV, GW. They are all part of the evaluation key, so they come from there. They are already the generator element to some power, and now this is taken into another power. So this is like a power of a power. So there is a lot of exponentiations going on here. And then the good thing again to note is that here in this, if you see this big block of values, it looks big on the screen, but all of them are individual values. So what is quite amazing, this means that the size of the proof is independent of the size of the computation. So the size of the proof consists of 1, 2, 3, 4, 5, 6, 7, 8, 9, of 10 values from this group, of 10 group elements. And it does not matter how big or complicated the program is, the proof is still of fixed size always. So that's, for me, this is the most surprising or amazing result that this is possible. It is possible to construct a fixed size proof of possibly unlimited size computation, that the computation was correct. I don't know. It doesn't really, in my mind, this just doesn't fit. But somehow they have pulled it off. And the verification is basically does two things. First, using those elements here, that proof contains those nine elements. I counted them wrong. There are 8 elements here. So I did something wrong on the previous slide. Yes, this one that I counted as 3, this is really a multiplication of 3 elements. So it comes out of the computation as just 1 element. So this is how I miscounted. So those 8 elements here, it is possible based on those, again, to compute a thing which comes out only correctly, only if this divisibility of those 2 big polynomials, if this divisibility property holds, then this element here and this multiplication of those 2 elements here, they map, they match, and roughly the reason why this holds is that this element corresponds to the big px polynomial, and this element corresponds to the tx, the smaller polynomial that has to be the factor, and the server was able to produce something that fits here, that represents the divisor, the result of the division of the p and x. So if you look here, then this hx is basically the result. If you take the px and divide it by tx, then hx is a result of the division. And here, roughly, this E applied to those elements here represents, corresponds to the polynomial px, and this corresponds to the polynomial tx, and this corresponds to the polynomial hx from the previous slide. And if this product here equals to this value here, then this means that those polynomials were actually constructed correctly by the prover, by the server that did the computation. And you would think, perhaps by default, that, well, these are just, basically these are just large numbers and you can fake them. But the problem exactly is that the server does not know. So the server has been given this value GV, but it has not been given the value V, the exponent. So there are things in this set of input data which are hidden from the server. They are represented indirectly. Those exponent values are represented in this set of data that the server was given, but they are in such a way that the server cannot extract them. The server would need to solve this discrete logarithm problem for that, and it is computationally infeasibly difficult to do. And the probability that the server would be able to just luckily guess or fudge the numbers, this is also extremely low, because again, we are talking here about numbers which are 200, 250 bits long. So the probability that you by trial and error find something that matches, the probability is so low. You would be trying until the sun goes out and you would still not be there. And by sun goes out, I mean not the sun sets tonight, but I mean sun goes out by blowing up as a supernova in a few hundred million years. So this is the kind of amount of work that we are looking at if we try to brute force a solution to this equation where we haven't really done the work correctly, if we try to fake a proof. And another thing that needs to be checked is that the assignments of the internal values, those CI elements, that those are, if the server constructs those V and V prime sets for the values of the wire assignments, and the same, so basically those checks here on this second bullet point, they amount to checking that the server has used the same the wire values in different places in those equations. So if we did not check for this, the server would be able to cheat by saying that the wire value, for example, this one value, let's say this value here, by setting it to 0 in some parts of the computation, and by setting it to 1 in some parts of the computation, and possibly by setting it to 7 in some other parts of the computation, and it would be able to create confusion. But those checks here, these are designed in such a way, again, that the probabilities that the server manages to produce the values such that those checks match or come out correctly, if it has not used a consistent assignment of those fixed assignment of those CI values, this probability is negligible. Again, this is if we are using 200-bit numbers, then the probability that the server would be able to cheat with those values here is something to the 2 to the power of minus 100. So the server would need to be do 2 to the power of 100 computational operations to be able to generate a fake proof. And this is considered decidedly impossible, infeasible. So this is a sufficient security margin against any size of computer that you can possibly build on Earth. So the last thing, private inputs. What if some of the input data to this function f is private? So a very general way of how verifiable computation on public inputs can be turned into verifiable computation on private inputs, and this now goes from math again into kind of hand-wavy territory, is that what you can do, you can compute the commitment of this private data. And typically when you operate on those private inputs, the thing that you want to prove is that you have done multiple computations using the same input. So you haven't changed your inputs between computations if you have promised to keep them stable. Like if you do multiple checks against the database and you have promised not to change the database in the meantime between those queries. So the recipient of the query results wants to be sure that the results are consistent with each other with the same state of the database. And this is typically done by taking the private data, computing a commitment of it, and publishing or posting the commitment. And then if you want to verifiably compute some f on this private data, then the generic solution is instead of just applying f to the d, is to make the server compute two things in parallel. First apply f to the d and then apply c to the d. And so basically the f applied to d is the function value that we want to compute, and then c applied to d recomputes the commitment, and then the client receiving this pair and verifying that the pair was computed correctly from the input d can check that the commitment value that the server computed matches what was published. So this is kind of very hand-wavy and rough explanation of how you can do in general case. Pinocchio actually has direct support for computing on inputs where where is this evaluation? Where some parts of this U come from the client and are visible to client, and some parts of this U come from the server and are not visible to the client, but the server can include in the computational process proof about some properties of those inputs that the server provided. So this enables things like privacy-preserving testing of database membership, where all police stations can send to the FBI queries about is this face on the wanted list, is this face on the wanted list, but the FBI doesn't have to share the wanted list publicly. So the FBI can put people on watch list without those people learning that they are on the watch list. So these kinds of things you can implement with those private inputs. And Pinocchio has direct support for those, which is more efficient than doing this kind of workaround thing. But this workaround thing is perhaps easier to understand, and it is more generic. This can basically be used with any verifiable computation framework, even if the framework doesn't have built-in support for partially private data. So this is how you can then do verifiable computation on private inputs using a kind of a zero-knowledge-like system. And some references. The underlying idea of representing computations as quadratic programs is from 2012 by Gennaro, Gentry, Varno, and Reikova. Gennaro and Gentry are IBM Research, if I remember correctly. I don't remember the other two where they are from. I think Varno is Microsoft Research. And then a year later, Pinocchio came out, which uses those quadratic programs to achieve all the things that we have been discussing today. And here I think, half of the authors are from IBM Research and half are from Microsoft Research. But since this is being recorded, perhaps I should not speculate who is from where if I don't remember it for sure. Anyway, you can click on the link and see the authors and their affiliations. And since 2013, there have been other developments, like I indicated before. So there has been a development of something called zk-snarks, which is also based on quadratic arithmetic programs. And then there are two new families of verifiable computation systems, zk-snarks and bulletproofs, which use a different representation internally. They don't work on arithmetic circuits. They use a different way of representing computations. But we don't have another 2 hours to go into those details. So the words are quite distinct. So if you are interested, then you can just Google. And there is the bulletproofs maybe is something that is the hardest to Google, because people might end up on dark websites trying to sell you fake bullet vests or something like that. But if you put cryptographic or verifiable computation or something like it next to it, then you're going to find the correct paper easily. So the question was, what subset of C was supported? I don't remember all the details exactly, but roughly you could do integer arithmetic. You could do conditionals, which were translated. You could do loops over like a bounded loops. If the compiler was able to unroll them at compile time, you could do those. I don't remember if you could do function. You could do function calls. So function calls were inlined. So you could do regular function calls, but not recursion. And so those were done by inlining the function at the call site. But the semantics of local variables and parameters was preserved. So the inlining was not done by kind of macro substitution. It was done more cleverly. So the compiler was pretty good. You could also use convenience features like name constants and things like that. There was no floating point support. This was listed as something that perhaps to consider for future. If you need to do non-integer programming, then you can somewhat simulate it with fixed point arithmetic. So instead of computing with integers, you can compute with thousands of the things, and you have this implied comma after the third digit. So these kind of things you can still do. And the integers supported were, I think, if I remember correctly, both signed and unsigned in 32 bits that they were able to compile into those circuits. Probably you could do larger ones also, but then you would also need to use larger elements in those algebraic data structures. So you need to use groups with larger things. And one of the things that they did for getting better performance out of those things is that they made use of the fact that for cryptographic security, you need to do those things on 200-bit integers. And if your application integer size is 30 bits, you can do a few multiplications without worrying about overflow before you have to do something to renormalize this back into the 32 bits values. So these kind of things, so they were tracking the number of bits that they were actually using in each integer and using that to optimize, because the renormalization step was one of the more expensive things. So I did sweep a few complications under the carpet here. I think the presentation was already quite complicated enough. So I really felt I can't put all the details in the presentation. That would have been too much. But yeah, good question. I should have actually included a slide on that. I just my mistake in not anticipating this.